Hello. So in this video, we are going to see the demonstration of how the working design for part 1 of our homework 5, which is the VGA-FPGA interface and the power estimation. So this first part of the assignment was about learning how to use the FPGA, so specifically the DE1-SoC board to generate the precise timing signals needed to drive the basic VGA display. And then here we have a Terasic DE1-SoC board again, so connected to a standard FPGA, standard VGA monitor. The VHDL design programmed onto the FPGA generates all the necessary VGA signals. To do this, we learned how to implement several key components. So we'll just dive into these. So this is the first part of the video, which I'm going to do it. So in this, I've already got the outputs. So this is what I had to implement using the board and then formatting the VGA output to the monitor. So this is the output I've received, and this is what I've done. I've configured it for the 1280 cross 1024 at 60 Hz resolution. So these are the compiling reports that I've received. It has used 35 nms, ALUT is being 51, and then critical path lag, maximum frequency, and rest of the parts. So we'll just go to the quartus prime. So we'll just close this. Yeah, so coming to this. So first we have to generate the PLL. So configuring PLL IP core, this Altera PLL core takes the 50 megahertz input clock from the board and generates the specific 108 megahertz pixel clock required for the target resolution. So that is all done, and it's all stored in the DCM altera.qip. And then we have this generic part where we are writing the VGA controller VHDL file. So this module uses that 108 megahertz clock to produce the essential horizontal and vertical sync pulses, the F-sync and V-sync pulses, and manages all the blanking intervals to match the 1280 cross 1024 at 60 Hz timing standard. So this is where we have written. So if you just see this is the resolution that we have used. Then coming to the generator, we wrote a module in VHDL. Its job is to control the RGB color values for each pixel during the active display time. So this is where we are going to do that. So our ideal output should be a blue and a yellow boxes, which is like there's a yellow background and you have a blue box on that on top left. So, and again we have the SDC file, which is for 20 nanoseconds, so 50 megahertz clock. So I've already compiled this. I'm not going to compile again because it's going to take some time. So I've got the report in this. So as I showed in the Word document that I've written, so this is all the compilation reports that I've got. ALMs being 35, then ALUT is being 51, pins being 31 again, and rest of the part. So now that we have already compiled this, we can move on to the programming part. So I'm going to use my phone to record for the programming part of it so that I can also show the monitor part. So yeah. Hello again. So this is where I'm gonna program the board. So I've already made the connections for the board. So I've already got a display, but I'm gonna reset it. So I'm just gonna restart the board and then program it. So it's already detected. I don't have to give the auto detect. So I'll just remove this and then add the updated SOF file. So if you can just see that it's already being checked. So this is the file that we are gonna load to the board. So I just click on the start. So if you can just see that board is being programmed and we should have the display set properly. So if you just see that the display, we have the yellow background and we have a blue square box on the top left, so which is needed as guided by the manual. So this display is being set for the 1280 cross 1024 at 60 Hz refresh rate. So and in the PLL we have used 74.25 megahertz, which is the desired frequency for this configuration. So we can also toggle the aspect ratio for this. So if we can just see, so because we have set for the full screen, we have the display for the entire thing. So if you just put on the original aspect ratio, you can see we have the black bars on the side because we are using for the 16:9. So we are just gonna put this back to the full screen mode. Yeah, this is our ideal output that was necessary for the part 1. So that's it. Thank you.